Hello, good afternoon. My name is Bollinger. I'm at STMicroelectronics and I'm in charge for imaging sensors, which is on one side time-of-flight sensors, consumer products, and on the other side CMOS camera sensors. I'm in charge for Central Europe, means Germany, Switzerland, and Austria. And I will show you in a few minutes how you can design a low-cost, portable, feature-rich, low-power camera. We don't talk about mobile phone cameras, we talk about cameras which are portable, which are low power, battery driven, and I will show you how many features, because it's feature rich, how many features we have implemented. So I will show you what kind of technology we're using, what are the target applications, and what makes our camera feature rich and low power. So ST has a long history in imaging sensors, CMOS sensors. ST was the Nokia camera in the 90s. So we built the Nokia cameras. After Nokia disappeared from the market, we have mainly designed automotive sensors. Automotive sensors are quite expensive because they carry all the automotive grade and are not sellable on the consumer and industrial market. And now we have restarted to design or to reuse automotive sensors. We removed the automotive grade, so the device became smaller and cheaper, but we have automotive technology, automotive pixels, which are at high quality. So this is our roadmap. We have already two. The third product is already also present. The G0 is a small 400 kilopixel sensor using already a 2.6 micrometer technology, BSI, stacked. So we have an optical chip and we have a digital chip. And now today we talk about this G1, 55G1, which is a 600 kilopixel sensor. And this is the one which we take as powerful, featureful, low power sensors for cameras be used in mobile applications, mobility applications, not mobile, mobility. So let's have a look to the feature list, just comparing the 400 and the 600 kilopixel sensor. You see the first line, the size of the pixel. So the pixel is already very small, but it's still high quality pixel because we're using trench isolation and backside illumination. The resolution is bigger than VGA. We compare ourselves a little bit to VGA sensors. And what is the main difference is that on the digital part, we have implemented a lot of digital features which implement something like an ISP, implemented, integrated, and we just need an MCU externally to drive the picturing and the streaming. This is a big advantage because this normally costs an ISP or this costs an MPU, and we have put this in the digital part of the sensor, and by this we have a quite cheap approach at high quality and very feature rich. So we look now mainly to the G1 600 kilopixel sensor, global shutter. In the past we did rolling shutter, but for the consumer market we are designing today only global shutter sensors, which are faster, more efficient. So this is the block diagram, and you see immediately all the digital part which we have implemented on top to the pixel array. To be true, these are two chips stacked together, bonded together. So we have mainly the pixel design on one side, on one chip. And on the second layer, we have the digital part where we perform cropping, binning, flexible gamma, the output interface, IOs, out exposure, MIPI interface, but also ICCC if MIPI is not existing, is not available on your processor side. So this is the basic block diagram. Again, to be true, these are two chips. So this can be one of the typical applications where such a global shutter sensor can be used. Augmented reality, mixed reality, so glasses, where you want to record something, where you want to display something in a glass, which needs to be low power, high performant, because the battery capacity is extremely limited, especially if we speak about small components with small batteries. So what we can do is we can do eye tracking, mouth, chin and cheek detection, gesture control, room mapping. So what is in the room, where are chairs, where are furniture. This is just an example how such a low power, feature-rich application can be done. So this is the key point here. This is a key point why we say the picture quality is at high level, because we're using trench isolation, so there is no crosstalk between the pixels. We are using backside illumination, means the light comes from the backside of the chip. There is no crosstalk on the metallization layer, and the quality for this is very high. This comes from our automotive designs. So this is, let's say, our history of the last 10, 15 years. Automotive pixel, but now available for consumer and industrial market. So here is a 3D, let's say a 3D design, how we share the functions in the chip or on the chips. There too. We have the imaging sensor with the pixel, and we have a digital part where we put all the digital functions like the ISP functionality, cropping, binning, the interfacing, this kind of things. Yeah. This allows us to use the full area, which is firstly dominated by the imaging chip, for digital functions. Yeah. And this is why we are able to integrate so many things. So just to explain, top layer is a 65 nanometer process optimized for pixel design. And the other one is a 40 nanometer design, 40 centimeter nanometer, where we use analog and digital functions to make it low power and feature rich. So what can we use and how can we use it? So since we have a higher resolution compared, for example, to VGA sensors, we can have a wider field of view. Just think about augmented reality, a glass where you want to see more. So having a higher resolution, you have a higher field of view and you can see more. This is key. This is important. Sorry, too fast. So let's compare ourselves a little bit to existing camera sensors like a VGA sensor. So our first product, we call it Foxy, this the 400 kilopixel sensor, has already a higher resolution at a smaller size. So we can decrease the size of the sensor, we can do it more cost effective, we can do it cheaper, and we have more resolution. Then next step, our 600 kilopixel sensor, even offering more resolution, 800 by 700, at a smaller chip size. So again, more features, more digital features, higher quality, lower cost, smaller design. Always comparing us to a standard competition VGA sensor. Yeah? Higher resolution, smaller designs. So this is a table just showing the advantages in the resolution and the advantages in the die size, in the size of the sensor, which is definitely smaller, cheaper, and better. So this global shutter sensor at the end gives you a higher resolution, a smaller sensor, more cost-effective sensor, low power application, feature-rich, and less noise, so better performance. So let's have a look to the digital features which we have implemented in the digital part. One key feature is binning and cropping. So we can do on a chip, just by programmed by the MCU, binning and cropping. We can decrease the picture, we can decrease the effective pixels by binning and by cropping. And by this we can reduce the, let's say, data which is transmitted. We can increase the frame rate. This helps to optimize the streaming of the picture. Again, digital functions fully implemented, no MPU needed, just commands, and receiving the picture. This is, for example, a picture where we use binning. So this is a picture which is not binned, 640 by 600, 200 frames per second. And once we start to do binning, we can increase the frame rate and be faster and transmit more data. So binning helps you to stream, let's say, lighter the picture without MPU. Still, I repeat, on MCU level. We are ultra low power. Means we are streaming in the range of a few 10 milliwatt, depending on the frame rate. Yeah? In full transmission mode, we need something like 20, 30, 40 milliwatt full streaming. And once we're using the low power mode, just supervising the scene, we take a few milliwatt. And the device itself can do an auto wake-up feature, means if a pixel is changing, if there's a movement, we activate the sensor, we stream, and we switch from a few milliwatt to a few 10 milliwatt for a full feature, battery-friendly streaming of the picture. And this is one of the key features that we can live with a battery. So just imagine the camera which is out in a desert, in the forest, watching animals, battery-driven, just streaming once the animal shows up, or the camera at your home, supervising your house, your apartment, just streaming once the burglar is coming. And then you're warned. Yeah? So low power, but really high quality, high resolution, so you can see the details, but at low power. Key point is battery-driven. So this is in auto wake-up mode, you see a few milliwatt, simply supervising the scene. And once we start to stream with this auto activation mode, we take a few 10 milliwatts only. Key point. Auto wake-up mode, I just repeat. So in the device, we have a circuitry which allows the supervision of the scene. If one pixel is changing, we activate. So we see the animals, we see the burglar, we see the thief, somebody wants to go into your house. High-speed interface. So our standard interface, because we are a camera sensor maker, is MIPI, the MIPI interface. ST has today also MCUs with MIPI interface, but depending on your background, you may have a controller system which does not have MIPI. This is not a point, this is not a critical point, because we have ICCC. The ICCC can be used to program the device, but also to read out the stream. So this can also ease your application. At least it doesn't make you necessarily use a MIPI interface, because we have MIPI for camera friends, and we have ICCC for MCU friends. Yeah? So both interfaces are available, making it flexible to use any kind of external MCU with or without MIPI interface. Okay. Next feature is differencing mode. So we take two frames, two pictures, and we compare them. If there is no difference, means the picture is still, we don't stream. If there is a small difference, like a moving packet on a conveyor belt, like a letter from your mail distributor, like a movement, like a gesture, we see the difference and we transmit the difference. So this only transmits the difference between two frames, two pictures, which allows you to see movement on the scene, packets, letters, hands, persons. And this is also decreasing the bandwidth, necessary bandwidth, because we transmit only the difference of these two pictures instead of both pictures. Okay? Difference mode, allowing this kind of activations and seeing the difference and displaying motion. Then, which is quite normal today during video conferencing, we can remove the background of the picture. So this is my colleague in Grenoble. This here is your office. Nobody should take care about your office, so we can completely remove the background and just transmit the face of the colleague for a video conferencing, this kind of applications. No? So this is supporting video conference assistance. This is enabling background blurring, just to make the background not visible. And this is again a feature which we have put in a digital part, which you simply can call by a microcontroller. Very simple, very easy. Then we can pre-program sequences, frame setups, contexts. So we can define up to 4 different contexts, so different settings of the sensor, and we can recall them. So if you have already in advance knowledge about what you want to take as a stream, you can pre-program them, different settings, frame lengths, cropping, whatever. You can program up to 3 of them, and you can recall them during the streaming. So during the streaming, you can change, let's say, the setting, which is also very easy. Again, it does not require an MPU. It's an MCU only. Then, of course, we have I/Os to generate interrupts, to start synchronization, this kind of things. These flexible I/Os are there, can be used, and they are again a part of the digital section of the chip, allowing simple MCU applications. What else? HDR. So HDR allows to have, let's say, overexposed pictures, overexposed scenes, like a room where you have a dark section, like a window section where it's very bright, and we can optimize to HDR the scene. So you see here a completely blurred picture, we can see here a completely dark picture, and during the process using HDR, we have at the end an HDR optimized scene, and you have a proper picture, and you can see really clear what happens in the room. So a room is just an example how HDR can be used. We have equivalent examples in the public world where there's sunlight, there's shadow, and we can optimize, in this case, the scene. Again, it's a feature which is implemented in a digital part, which doesn't cost you an ISP. In the past, we were using ISP to do these features, and which still requires only an MCU. So how do we support you? ST itself delivers only the wafer, the chip, raw wafer. And your customers, or you as a customer, have to take care how the camera is built. ST has partners, and these partners are able to deliver modules. So the camera bonded in a housing, a module, an optical module on top, and then a connector flex cable. This is just one example of a partner module which you or your customers can buy and can source. One partner is in China, one partner is in Israel. They have more, let's say, off-the-shelf solutions of camera modules. And we have a third partner here in Germany, it is Jabil. You know Jabil as an EMS, as a manufacturer, but Jabil has also an optical department. They are located here in Jena, so the optical headquarters of Germany. And they can design for you or your customers modules on request, depending on your optical requirements, depending on your connections which you use for your, let's say, application. So they can design these cameras. And you see the camera is extremely small. If you visit us on our booth just around the corner, I can show you the samples. They are in the millimeter, square millimeter size, extremely small. Yeah? I remember the Nokia camera at that time was 6 by 6 millimeters, and this is nearly the same size. Yeah? So we can sample camera modules, but we don't deliver in volumes. For the volumes, we have our partners, but for demo board activities, for sampling, we can provide you some 10, 20 samples. After that, you have to refer to our partners. How do we support your application? So we have a demo board, the square. On the demo board, we mount one of these partner modules, 600, 400, 105 megapixel. And you can connect it directly through USB to your laptop using a GUI, so you can explore the features through a graphical user interface. Once you want to program, you just add an additional board with a controller, and then you can start to build up your own application based on our software, based on our support. So these are new demo boards which are just now ready to be delivered. They are now diffusing to our distributors. But these are the new boards which makes our life a little bit simpler because we have only one demo board and we just add the modules, the optical modules. Okay, that's all. So ST has today 3 camera sensors, 400, 600 and 1.5 megapixel. We are now restarting, reusing automotive technology, automotive quality, and we are able to add digital functions because we're using a stacked 3D design, an optical chip and a digital chip on the bottom. If you want, we can continue discussing on our booth, which is just around the corner. Any questions? I open for questions, please. No, thank you very much. As I said, you're invited to visit our booth where we can discuss any kind of sensors. We have MEMS sensors, we have CMOS sensors, we have time-of-flight sensors. If you want, you can visit us. Thank you very much.